Get rid of that. Right, welcome everybody to the next edition of the INQA seminar. So this week we have Antoine and Michel, who is going to tell us about Hubbard physics with Rydberg atoms using quantum spin simulator to simulate strong fermionic correlations. So please, Antoine, go ahead.
Thank you. I want to thank the organizer for inviting me to this seminar. So this work I will present here has been done at EDF, so where I work during my PhD, in collaboration with Institut d'Optique at Palaiseau, Eviden, and the Quantum Startup Pasqua. So to start, just a few words about quantum computing at EDF. So EDF is one of the biggest energy supplier in the world, and the goal of EDF is to deliver a sustainable and CO2-free energy. And of course, as one of the biggest energy supplier, EDF is facing many challenges. And 5 years ago, approximately, they started to ask themselves, can quantum computing or quantum simulation help in some fields? And the answer is yes, in a lot of fields, in fact, in optimization, for instance, partial differential equations, and a lot more. But today we will focus on material simulation. So at EDF, we have a big problematic of materials aging. For instance, in nuclear power plant, components undergo harsh environment in terms of temperature and irradiation. And the main goal of EDF is to anticipate aging of these components and being able to say if they will crack or not after 80 years of work. And to do that, we perform atomic scale simulations. So state-of-the-art simulations to solve the Schrödinger equation. So for instance, the density functional theory is used to simulate defects in microstructure and everything with it. And also to go at the scale of length, which is of interest, they use a kinetic Monte Carlo and molecular dynamics. So these methods bring a lot of progress over the last decades, but some limitations exist in specific cases. For instance, in the condition of nuclear power plant, austenitic states are paramagnetic, and it is a state that is very difficult to simulate with DFT, which work at 0 Kelvin. We can also think of strongly correlating interactions, for instance, in batteries. So batteries are very important at EDF also to store energy and to regulate the frequency of all the electrical network of France, for instance. But there is also a problem to compute exact states. We can think of photovoltaic panel. So these are the main limitations of the numerical simulation used at EDF. And we need to go further, and that's why we are using quantum simulation. So of course, you know that we cannot simulate bulk materials with defects today with a quantum computer, but we can start to think about some toy model in physics. And one famous toy model is the Fermi-Hubbard model. So here I will focus on the 2D lattice. So this model is quite simple as it involves a lattice on which electrons can jump with a probability T, which is the kinetic energy of the electrons. And also the electrons don't see each other until they are on the same site. And when it is the case, they interact with the Coulomb interaction. So it's the interaction term U. It's a toy model. It means that it's quite simple, but it is physically relevant for many problems. For instance, high temperature superconductors are based on this model, and the community thinks that solving this 2D model in some doping and temperature will help to understand superconductors. It can also be used to study Moiré materials and so on. So it's a toy model, but not so simple. And it has not been solved yet exactly on the 2D lattice in some regime. So to study fermions, usually what we do is using a mapping between fermions and qubits. For example, the famous Jordan-Wigner transformation allows to go from fermions operators to qubit operators, so Pauli matrices. But this transformation comes with loss of locality, for instance. So it comes from directly from the Pauli principle. And also, it is difficult to perform this mapping into 2D and 3D, especially for the Jordan-Wigner one. So maybe we can think on another way to transform fermions into qubit or spins. And also, usually, people and researchers are using variational approach to find the ground state energy of a system. So it has been done in several work with good results, but some questions are often asked, like, do you have a barren plateau? So how do you know that you will converge towards the real ground state energy? Which of the classical optimizer you are using, variational approach, and so on. And in this work, we have tried to not use this approach. And that's why we have used the slave-spin method. So here I will introduce the slave-spin method. So it's condensed matter tools used by theoreticians like 10 or almost 20 years ago. The idea is to take the fermionic creator operation and add it, for instance, a slave spin. So we enlarge the Hilbert space, and with that we impose a constraint on each side of the Fermi-Hubbard model to impose that the states or the states available or the physical states. So for now, we do not make any approximation, and this Hamiltonian with combined with this constraint is an exact formulation of the Fermi-Hubbard Hamiltonian. Now, the main idea is to perform a mean field decoupling between the slave spin degrees of freedom and the fermionic degrees of freedom. And now we get a sum of fermions and spins, which are decoupled. And the constraint can be now applied at the mean field level. In our work, we studied the one band square lattice Fermi-Hubbard model at half filling. It means that we have the particle hole symmetry, and in this case, this relation is fulfilled directly. So we do not have to take into account the constraint. But it is because we have the particle hole symmetry. So we start from the Hubbard model expressed within the slave spin approach. And this Hamiltonian can be approximated after the mean field decoupling into a sum of a free fermionic Hamiltonian and a spin Hamiltonian. So in fact it's a strong transverse field Ising model. And now the idea is to solve first the fermionic Hamiltonian with a classical computer. So it's free, so it's only polynomial in complexity. So it's quite easy to compute it on a classical computer. Then we get fermionic correlators, which will be add to the spin Hamiltonian. And the spin interaction in the Ising model will depend on these fermionic correlators. Then the idea is to solve these spin Hamiltonians with a quantum computer or quantum simulator to obtain the spin-spin correlator, which will be added to the fermionic, free fermionic Hamiltonian. And then we get a self-coherent loop until convergence. So we calculate, it's like an hybrid approach. We calculate classically a correlator that will be injected in the spin Hamiltonian, which will be solved using a quantum simulator to obtain the spin-spin correlators, to inject it in the fermionic Hamiltonian, and so on. So with this method, we are able to study the Hubbard physics on the spin model. So by measuring the magnetization, for instance, we are able to recover the phenomenology of the Fermi-Hubbard physics. If we want to study the Hubbard physics, it's quite good to see some phase transition, for instance, but to do that, we have to go at thermodynamic limit, which is impossible, of course, on a quantum simulator. So to solve the spin Hamiltonian, we use what we call the cluster mean field approach, what is called the cluster mean field approach, so developed here in 2010. The idea is to take only a small cluster of the spin system and to say that this system is surrounded by a bass, a mean bass of magnetization, a mean magnetization. And so we can perform also a self-coherent loop to study this model by calculating the middle value of magnetization along the z-axis in a self-coherent manner to obtain the spin-spin correlators. So at the end, what we want is to solve this spin Hamiltonian, which is a transverse field Ising model with a longitudinal field, which comes from the cluster mean field approach. So now that we know what is the target Hamiltonian we want to solve, I will briefly describe the Rydberg quantum platform. So I'm not an experimentalist, so I will not go into detail, but I will give you some physical relevant details to be able to understand how we solve the Hamiltonian I talked about. So the Rydberg quantum platform is based on neutral atoms, which are controlled by light. So we can control the atoms one by one and play and construct arbitrary geometry. So for instance, here the square lattice geometry, but also triangular, everything we want in 2D. And the idea is to take two states of two electronic states of the atoms. So for instance, the ground state, which will be the 0 qubit, and the Rydberg state, so highly excited state of the atom, to be the qubit one. So these two states are coupled. And with that, we have a phenomena called the Rydberg blockade, which means that when the atoms are within a circle of radius or B, the atoms will not be able to be collectively excited. This means that within this circle, if two atoms are in the ground state, if you want to excite them at the same time, they will not be excited and they will not be able to reach the Rydberg state. Instead, they will reach the plus state, which is a maximally entangled state or rebel state. So taking into account the Rydberg blockade, we are able to simulate interacting spins and reach exotic phases of matter. So there are two Hamiltonians that are simulable on this platform. So first, the Ising Hamiltonian. So I will focus on this one. I have focused on this one during my work. But also the XY Hamiltonian. I will not go into detail for this one, as it does not involve the same physics. What is important here is that the transverse field of the Ising model on the platform and the longitudinal field can be controlled with a laser and microwave. And it is really important because we are able to evolve our system with a parameterized Hamiltonian. So let's go back to the target Hamiltonian we want to solve. So the spin Hamiltonian from the cluster mean field approach of the spin method. The idea now is to solve this Hamiltonian with the adiabatic theorem and annealing. So we prepare our atom in the ground state, and we consider an Hamiltonian that has a ground state which is the state 0, 0. So we are in the ground state of this Hamiltonian. And then we drive the parameters, so omega and delta, so Rabi frequency and tuning, slowly enough to reach our target Hamiltonian and to stay approximately in the ground state of this target Hamiltonian. So of course we have to go slowly enough, but yeah, it is working for like 15 atoms, as I will show just after. So now some results on the Mott transition. So as I said, when U is equal to 0, so we don't have interaction in our system. The system is a 2D metal, so we have 3 quasi-particles. On the other hand, when U is very large in comparison of T, the system is a Mott insulator. It means that electrons don't want to jump on the lattice, and everything is frozen, basically. And we can measure the order parameter of this phase transition on the quantum Rydberg platform. So the quasi-particle weight within the spin theory is only the mean magnetization of the atom in the z-axis. And we can perform, so here it's a perfect simulation without atoms, without anything, just a perfect simulation of the spin method to show you that we can recover a phase transition. So of course, the transition value depends on the number of sites we are taking into account. But when U over T is small, Z is non-equal to 0, and then we have 3 quasi-particles. And when U over T is larger than a certain value, Z equals 0, and the system is frozen. We are in the Mott phase. So with this method, we can recover qualitatively the Mott transition of the original model. It's quite the same result that has been found by people using the spin method. So now, what if we take into account the noise inside the Rydberg quantum platform? So of course, we are in the NISQ era, and we have to take into account noise. And for my numerical simulation, I used several types of noise. So for instance, dephasing for the laser which are controlling the atom. Error rate in the measurement. It is possible to measure 1 instead of 0 and 0 instead of 1. Also, we have only access to a small number of measurements at the end of the annealing procedure. Of course, we do not have access to the full vector state because of projection of the state. So I have bounded my measurement to 150 at each time step. And also the time of annealing is limited, of course. We have a coherence time of our atoms, and we cannot perform annealing during a time which is too large. But despite all this source of error and all this noise, we can recover here in the full lines qualitatively the same results as the perfect simulation. So here I have performed the simulation with some noise, and we see that we can recover, at least qualitatively, the phase transition. Okay, so we are happy, but this type of calculation and measurement can be done classically with classical method. So if we want to reach or to getting closer to a quantum advantage, we have to study the dynamics response of the Fermi-Hubbard model. So here what we are doing is solving our model with no interaction, u equals 0. And then we switch on abruptly the interaction for a large value, or for a value which is not 0. And then we observe through time how the quasi-particle weight behave. So what we see is what we call a collapse and revivals of the quasi-particle weight. It means that after the interaction is switched on, we observe oscillations of the quasi-particle weight through time, which is in agreement with experiments and perturbative analysis. In the literature, they observe this type of oscillations. And what is interesting is that these oscillations have a frequency which depends on the strength of the interaction quench. So it is shown here. So we have plotted the frequencies of oscillations as a function of the interaction quench, and also the amplitude of oscillation. And we see that for a strong quench, means that a quench which is far away from the transition value of the interaction, frequencies are equal to the interaction quench. On the other hand, when the quench is smaller than the transition interaction value, we see a quench which is approximately equal to we see a frequency, sorry, which is approximately equal to the quench over 2. This is something that is observed in the literature, and which is quite well explained with the physics of the Fermi-Hubbard model. So we are happy because we can recover the physics of the out of equilibrium of the Fermi-Hubbard model with this method. And the quench dynamics is very challenging for state-of-the-art methods, for instance, for Thomson networks or variational Monte Carlo, because of entanglement and entropy, which is growing through time. So now the question is, are we able to go further than classical simulation? So the answer is we don't know yet, but an experiment on a real Rydberg quantum platform is planned to answer this question. So to conclude, the self-spin approach can be implemented on Rydberg quantum processor. We are able to recover the phenomenology of the Fermi-Hubbard system. When we consider noise, realistic noise, we still have qualitative results, and we still have access to the phenomenology of the Fermi-Hubbard model. And also, this method can be used to study equilibrium and out of equilibrium behavior of the Fermi-Hubbard model on a Rydberg quantum platform. So what are the next steps? So perspectives of our work. So we aim at performing the same simulations for different geometries. So as I said, we are considering in our work the square lattice, but what about triangular lattice, hexagonal lattice, and so on? It is also possible within the self-spin approach to study the multi-orbital Fermi-Hubbard model. So in that case, the constraint will be harder to fulfill, but it is possible. And also we want to study 3D systems, and we are thinking on how to implement this method on the Rydberg quantum platform for 3D models. So we have some ideas, but yeah, we need to push them to being able to simulate material of interest for EDF in the short term. Thank you very much, and I want to also to thank every collaborator and the co-authors of the paper.
Great, thank you very much for a lovely talk. We can now invite questions. So please, Joseph, please go. That looks like applause coming up. Applause or raised hands? I can start.
Just an applause. Thanks.
I can start with a question. So this slave spin model that you've introduced, and then you've got the mean field approximations and you're iterating, right?
Yes, exactly.
So is it known for sure that the iteration converges well?
That's a great question. It is not sure, in fact. We tried, we use some tricks to be sure that it will converge. For instance, we use the results of the step k iteration to be the starting point of the k+1 iteration, for instance, or things like this. But in our case, it converges. It is not sure that it will converge when we are in, I don't know, a multi-orbital model or the doped model. It's still an open question, I think.
Okay, because it's a very nice model and it maps very well to the spins.
Exactly, that's why we have chosen this one, because we avoid any kind of transformation.
Yeah. No, so it looks very nice, but then I'm looking at this cycle round and going, okay, that's great, but
in our case it converges, but
I mean, often it's the case that you can tell numerically that it's converging. Right?
Yes.
Even if there's no proof that in principle it has to. But also there's how fast it converges. I mean, how many iterations do you find you have to do?
It depends on the size of the system, of course, but not so. I mean, 20 iterations or enough in many cases, so it's not that big. After that, when we are considering noise, of course, we need more iteration because we have some errors, but we imposed a limit of 25 iterations, I think.
Cool. I'm keeping an eye to see if we have other questions in the audience. So, I mean, my other question is now about how the lattice, the spins, the arrangement of the spins, so therefore the Rydberg atoms.
Yes.
How does that relate to the geometry that the electrons are in? Is it completely one-to-one that you build the lattice you want and the Rydbergs are like playing the role of, you know, this in the same position as the quasi-particles, or do you have to do some mapping there?
Okay, so it depends. If you consider an infinite system, yes, it will be quite the same mapping. It will be a square lattice. In our case, it's not infinite, so you have, of course, boundaries, and due to these boundaries, here I've shown a lattice. So we have to, depending on the value GIG here, we have to optimize the geometry of the atoms, and here it's the geometry before optimization, and here it's after optimization. So you clearly see the effect of boundaries. But as we go, as we're growing in number of atoms, I think it will be more and more smooth. I mean, in terms of the square lattice.
Yeah. So basically, you have to put the Rydbergs where they will do the Hamiltonian, but exactly. The Hamiltonian terms, you have terms for neighbors, right? Or where,
yes,
where but you're modeling how the electrons move, but you're not moving the atoms to do it. So it's somehow the atoms of the lattice, and the state is showing you where the electrons would be.
Yes, it's quite like that.
Yeah, because again, something intuitive that you can draw the pictures go easily from between the picture of what you're simulating and the picture of what you're using. Very nice tool to use. Yeah. So, cool. So how do you know how big you think? How big a number of Rydberg atoms would you need to do something really interesting, if you like? You know, I won't say useful. I just say something where you're feeling like, yeah, I'm really learning something from doing this.
I think from like 60 or 80 atoms, let's say 100 atoms. I think we are starting to reach what for instance, tensor networks are able to do. So a question we want to answer also is the correlation length of our systems. So because if we can have a correlation length which is very big, so if it is like for 100 atoms, it is quite sure we will beat a classical simulation, because classical simulation cannot reach this kind of system. So I think, if we have 100 atoms, we can start to think on, okay, with noise, can we, because the noise will decrease the correlation length. So can we still beat the classical simulation? So that's why I'm looking forward for the experiment on a real machine to try to answer these questions.
Yeah. No, this is very interesting. I'm a theorist, but we have also at Strathclyde, we have experimentalists who do Rydberg atoms.
Okay.
Like this. Yeah. So it's, I'm very familiar with what you can do with them, but this is a new application, so it's very nice. Yeah. So
thank you.
Do we have more questions from the audience? Everybody is a little bit shy, or maybe no, we will say you explained it so well, they do not need to ask questions. So, so in that case, a big thank you again for taking the time to do the seminar for us.
Thanks to you for inviting me.
Yeah, it's very nice to hear all your work, and in, I think, a few minutes or so. I mean, we can log off now, and I will send an email, and Paul will come and shut it down. So more applause.
Okay. Thank you very much.
Thank you very much indeed again.
Okay. So
Yes, you can stop sharing.
I can stop sharing. Okay, nice. Okay, and you can see, of course, the paper on archive.
Yes, yeah. That would be.
There are a lot more. There are more details, of course, in the paper. Thank you very much.
Yes, thank you.
So
Feel free to. Yeah.
I can log on. Thank you. Bye.
Thank you. Bye-bye.
Bye.
Okay, thank you.